Our sixth presenter is Jonathan Shulgach, whose presentation is titled Faint Muscle Signal Detection Using Flexible Electronics, Invisible Movement, Visible Impact.
How many of you here have used your hands to tie your shoe or button your shirt today? How many of you have used your phone in the past hour? Now, imagine doing those things, but your fingers are paralyzed. For almost 5.5 million people in the US living with some form of paralysis, this is their everyday reality, making everyday tasks like these constant, permanent struggle. But what if it didn't have to be permanent? Medical tests often equate no visible movement with no control, but that's not always the case. For decades, electromyography, or EMG, has been allowing us to study those signals in our muscles using sensors on the skin. Clinicians use EMG to study human biomechanics, and even companies like Google and Apple integrate EMG into wearables to measure fatigue and stress. But for the people who could benefit from this technology the most, prosthesis users, individuals with spinal cord injury, exo devices that help basic movement, the technology is still somewhat limited. Commercial systems can only record from a handful of muscles at a time. And higher density systems do exist, but can cost upwards of $100,000 and be restrictive and too fragile for home use. So without an easier way to capture those signals, we'll never be able to fully match the natural dexterity of human movement. That's why my research focuses on designing flexible, high-density EMG systems able to detect and amplify those weak muscle signals for use in prosthetics, assisted devices, and rehabilitation. Inspired by rapid prototyping and flexible electronics, I designed my own system that not only matches the signal of our gold standard clinical EMG systems, but at 2% of the cost. And I'm not the only one excited about this technology. 4 other research institutes reached out to us asking to integrate my system into their studies. And our collaborators at UC Davis are integrating it into prosthetics for children born with congenital limb differences. It's not enough to pick up the movement. It's about restoring the natural movement. Nearly half of all smart prosthetics end up not being used, not because they fail, but because they're too hard to control. My research hopes to change that by making current and future assisted devices easier to use. With modern technology, we can redefine what's possible for restoring movement. All we have to do is reach out and grab it. Thank you.